In this video, we're going to cover how to calculate the derivative of an arccosecant function. So, d by dx of an arccosecant function is negative 1 over the absolute value of x times the square root of x squared minus 1. So when you're actually performing the calculation, the way you're going to look at it is the derivative of arcsecant x is equal to negative 1 over the absolute value of x times the square root of x squared minus 1 times dx, or in other words, the derivative of an arccosecant of whatever is in the arccosecant bracket, we'll call box here, is equal to negative 1 over the absolute value of whatever is in that argument, whether it's x, y, x squared, tan, whatever, squared minus 1 times the derivative of that argument. So to demonstrate that, let's look at an example. So we're given a function here, h at x is equal to the arccosecant of 2x. So in order to evaluate the derivative, what we would do, okay, the derivative h prime at x, which we can also write in Leibniz notation as d h at x by dx, is equal to this right here. So negative 1 over the absolute value of this term here, the argument, in this case it's 2x, so times 2x, times the square root of 2x squared, so 2x enclosed bracket, or enclosed in a bracket, squared minus 1. And then what we're going to do is we're going to multiply this by the derivative of whatever this argument is. In this case, it's 2x. So the derivative of 2x is just 2. Right? So that's basically the answer there. Of course, what we can do is we can simplify it. So what we can do is we can write it this way. And now one thing to notice too is like the 2's cancel out here. So we can write negative 1 over x times the square root of, and then we're going to expand this bracket here, so we're going to bring the exponent into the x, and then we're going to square the 2 as well, so that'll be 4x squared minus 1. So that would be the answer for that particular function. So of course we can do another example here, which we will do here. I'm just going to make some space here. So let's say we're given another function, which we'll call f at x, and we'll say that f at x, be a little bit more consistent here with the colors, f at x is equal to the arccosecant of the cotangent of x. Okay, so here, as you can see, we have a slightly trickier argument here. So we have a function within a function within a function. But again, that doesn't change how we evaluate the derivative. We're still using the same steps, and it's not something that's going to be too difficult. So we'll say f prime at x, which we can also write in Leibniz notation as df at x by dx, is equal to negative 1 over the absolute value of that argument. Like you have cotangent x, which is just cotangent squared x, cotangent squared, or sorry, no, not cotangent squared, just cotangent x, excuse me, times the square root of cotangent, okay, x, and we'll square this cotangent, minus 1. And then we'll multiply this by the derivative of cotangent x. Okay, that's where that comes from, is this right here. So the derivative of cotangent x is a cosecant squared x. Okay, or sorry, negative cosecant squared x. So negative cosecant squared x, and then we're going to multiply this by the derivative of the x, which is just 1. And there you have it. And of course, what we can do is you can simplify this. So as you can see here, the two negatives cancel out. So in the numerator, we're just going to have cosecant squared x divided by cotangent x times the square root of cotangent squared x. That's another way to write this term here. So cotangent squared x minus 1. And that would be the final answer here.